In this module, we're going to learn how we use GIS as well as drones to support our cut-fill operations. To be specific, we're talking about landfills and borrow pits. Now this here is Benton Crossing Landfill and Borrow Pit. Now this landfill here, as of December 31st, 2022, it closed. It's no longer accepting garbage. And what we have to do now is we have to close it out to a final grade that was created by some engineers. And we have a borrow pit to take dirt from and a landfill to add the dirt to so that we can create the final grade. These here are the programs that we're going to use to accomplish our task. For our photogrammetry, we're going to use AgiSoft Metashape. We're going to use Drone Deploy for our flight planning. We're going to use ArcGIS Pro to do raster calculations and visualizations. And we're going to use just a standard retail DJI Phantom Pro to fly the project. Very first thing we're going to want to do is set out our ground control points, permanent ground control points. I say permanent because these are points that we're going to come back to time and time again every time we fly this, and we don't want to have to do a resurvey every time. We just want to survey one time, set the ground control points out, and use them indefinitely into the future. And well, if you see here, these are where my ground control points were set out. A lot of people ask, you know, what's the best method for setting up ground control points? How dense do they need to be? I don't know. Every instance is different. I could say that what you want to do is set them out around the barriers, around the edges of your site. Think of it like a tablecloth where you need to cinch the edges down, and try and put a few in the center if possible. But this being a landfill and a borrow pit, there's heavy machinery constantly digging and moving the earth and changing things. So trying to set out something permanent in this type of site could be difficult. I was lucky that I found one area that was already at grade that they didn't intend to do any more grading on, so I was able to put a ground control point in the middle there. But generally speaking, you're going to get high accuracy data with your ground control points set out like they're at, right, like you're looking at right now. Then I'm going to set up my flight plan in Drone Deploy. Now you don't have to use Drone Deploy. There's many flight planning applications out there. This just happens to be the one I choose to use. And the way I do this is I go online for free to their website and I set up a flight. I draw out a rectangle around the area I want to fly. I tell it how high I want to fly and what my overlap is going to be, and it does the rest. It tells me how long it's going to take. It's going to tells me how many images I'm going to have, how many batteries it's going to take, and then I download this to my Android phone via the web, and I go out to the field and I just press a button, and what's really cool is the drone just flies by itself. It just flies this path on its own. All the operator has to do is stand by and watch and hope everything goes okay. And after the drone has had a successful flight, I am then going to download the images to my photogrammetric processing application here. In this case, I'm using AgiSoft Metashape. However, there's many. Esri has one called Drone to Map. There's one called Pix4D. They all generally do the same thing. And what they do is you add the images and your ground control points, and using the procedure laid out in the tutorial. One thing I like about this is the tutorial is straightforward and easy to follow. It works with any application. And from that, I'm going to get some products. Now, one of the products that we get is a high-resolution ortho image. In this particular case, the high-res ortho image has a ground pixel resolution of 1.9 centimeters. As you can imagine, that's a huge file size. Another product, the one we really want in this case, is the digital surface model. And I have specifically made the ground pixel resolution 1 foot because it makes the math easier. We also get a dense point cloud in a LAS format, similar to the same format you would get when dealing with LiDAR. Another product you get is a tiled model. Now, I haven't found many practical purposes for this except that you could make these really cool fly-throughs, and you could make these animations like you're watching right now. Now, another step in this process is to create your final surfaces. Now, remember, we're doing cut fill operations, so we need an existing surface and the final surface. And in the case of our borrow pits and landfills, we have specialized engineers, solid waste engineers, who designed our final surfaces for us, and they gave me contour lines, and from those contour lines, I then created the tin, and then created the DEMs, and it's the DEMs that we'll be using to compare against the DEMs from our drone flight to look at things like volumetric calculations and distance to final grade. Now that we have our existing surface that we created with our drone and our final surface that we created from contour lines, we bring these two surfaces into, in this case, I brought them into ArcGIS Pro and did a little math, and I created a difference raster. And from the difference raster, we're able to create some deliverables. Now, the guys at the landfill, they like this type of deliverable here. They like to see round numbers telling them how many feet they need to pile dirt on until they hit final grade, or how many feet they have to cut down to. And they also like to see the colors telling them whether they're above or below final grade, or in this case, the blue means they're right around final grade. And here's another deliverable for the borrow pit. We see the boundary of the borrow pit, and once again, we have nice round numbers telling them how far they have to go to dig down before they hit final grade. There's something else that the folks at the landfill like to know is how much dirt they have. So in this case, we just take that same our same final grade and existing grade rasters, and we run them through a tool that creates a volume. And here, using the volume tool, we see that we still have about 744 cubic yards to go before they hit final grade. That's a lot of dirt.
That's a lot of dirt.
Last but not least, should you have to do accuracy assessment, what you would have to do is when you're flying your drone, you would place additional ground control points out to use as testing. And you would test what the drone says the coordinates are versus what the GPS said the coordinates are. And what I do here is I have a spreadsheet that tests ASPERS and NSDA accuracy standards for vertical and horizontal by inputting the desired accuracy as well as your data, and it'll tell you whether or not you meet the standards.